Okay, so yeah, this is the final lecture in which we want to really like go dive into a topic, and the topic of this lecture is codimension 0, cohomology of gamma and p. So maybe let's quickly recall gamma and p. That's the principal congruence subgroup. So it's all of those matrices in SLNZ such that A is congruent to the identity matrix mod P. Yeah, and so the goal is, so the main question is, what is this is the top dimension. What is this? What is this? And so you might say, oh, we have a presentation of Steinberg. So, I mean, we know that this is H naught of gamma n p with coefficients in Steinberg. Now, this is actually true integrally if p is bigger than p is at least 3. This is by Borel-Serre duality. And you might say, oh, we have a presentation. So you can just compute that. So let's follow this idea. Let's follow this idea. So first idea is, well, I mean, we just want to understand this. This is actually Steinberg with co-invariance in this group. That's the same thing. And well, we have Bukowski's presentation. What did that say? It says C n of BA n of Z, comma BA prime n of Z goes to Cn minus 1 of this relative homology. C goes to Steinberg. And so this is a result, this is a presentation of Steinberg, and now we know that taking co-invariance is right exact. So we have a presentation of the co-invariance by taking Cn. Okay, I'm just going to abbreviate. I'm going to leave the Z out of this for now to have a little bit more space. Gamma np Cn minus 1 Ban Ba prime n gamma np goes to Steinberg Q co-invariance. Yeah, so we have a presentation of this, and I mean, you might say, okay, now I have to find the co-invariance of something else. I mean, before I had to find co-invariance, now I have to find co-invariance. Does that make anything easier? And it does make something a little bit easier, because really, if you take co-invariance of a Fourier being group where the group actually acts on the basis, then you can just take the Fourier being group on the set mod the basis. So this turns out to actually be the same as Cn of Ban mod gamma np rel BA prime and mod gamma NP, and this n minus 1 BA n mod gamma NP BA prime n mod gamma NP. So, and furthermore, where BAN mod gamma NP, let's say here in parentheses prime, is a finite simplicial complex. So that's actually quite nice now. Suddenly we have finite simplicial complexes, and all we need to do is find this homology. That's actually something that can be done by the computer, maybe. That's good. Yeah. So case closed. We're done for this lecture? Surely not. There's still some minutes to go. Maybe not. Why not? What this actually turns out not very computable. I tasked Graham to compute one of these things and some of these things. And did the P=7 case actually finish? Yeah. So I asked Graham to look at n equals 3, and then p = 5 was done fairly quickly, but p = 7 didn't even finish overnight. So this I mean, it's finite, but maybe it's really big. So is this really a good answer? Is it not? It is an answer, but maybe not. So for example, the dimension stays mysterious. Curious. So let me present you with another idea. So here's another idea. And in some sense, this idea is due to Lee and Sharber. It's curious. This is all in one paper. They have like 5 different results that I keep on citing, all in the same paper. I mean, all of them, the Sharpley complex is in there. The result about codimension 0 of SL and Z. Then they have this approach which they use to prove the codimension 0 for gamma and 3, which I'm going to say in a second. They compute H1 of SL and Z in that paper, and they also do some codimension 0 computations for n = 3 for more primes in that paper. It's completely insane what they do in this all in one paper. It's somehow works all together, but this is quite the paper. So what's the idea? Let's take the Tietz building, and then certainly there is a map from the Tietz building to the Tietz building mod gamma NP. And again, this turns out to be a simplicial complex. Now if I take homology of this, I have a map on homology. And in fact, this simplicial complex turns out, so it's also n-2 dimensional simplicial complex, and it is also n-3 connected. So really, this is the only homology that there is in this complex. And we have this map, and of course, this is the Steinberg module. And on the space, we have the action of gamma and p, and we mod out by this action over here. So this means this is an equivariant gamma and p map, a map that's a gamma and p equivariant, sorry. And on this side, you have the action still, and that's what you want to do, right? You want to mod out by this action to get a to get the quotient being the co-invariance. Or I guess this works for any gamma. Let me actually just say for any gamma this works. And now over here you mod it out by that gamma action. So this is trivial. So this factors through this map, and this is maybe this is kind of like a universal property of covariance. This always has a map to every trivial what do I want to say, a trivial gamma module. Okay, so there is this map, and the question is what happens with this map? Why do I bring this map up? Well, Lee and Schaber prove that for p equals 3, this map is an isomorphism. So they prove ST and Q with gamma and 3 to H and -2 T and Q mod gamma and 3 is an isomorphism. And I mean, in their case, this turns out to be pretty easy. This turns out to be just the Tietz building of F3. And so this means this whole thing is isomorphic to Steinberg of F3. So this is now this has dimension of this is a Fourier group is 3 to the n choose 2. That's something we know about Steinberg. And they ask, hey, is this an isomorphism for all p? Is this an isomorphism maybe for all gamma? It's a reasonable question to ask. And well, let me tell you about a theorem. Finally, I can present one of our own theorems. This is with Jeremy Miller and Andy Putman. So we take P as a prime. Just to be sure, I guess I always do. Then this map, which I guess I can write as from here to here. Mod gamma and Q. This map is always surjective. This map is for P at most 5, and it is injective. So this includes Lee Schaber's result for 3, and maybe their techniques also show it for 2, but certainly not for 5. For 5, it's much more complicated. And then for P greater equals 7, it turns out that it is not injective. And let me maybe include n is at least 2 here, so to take away some of the, I mean, if n is 1, all of these are like trivial groups and stuff, so there's not that much information there. Okay. So this is the result that I want to talk about. Now, well, you might ask, so as I said, p equals 3 was known, p equals 2 is probably can be considered to also be known, maybe because it can use the same methods. That would also be Steinberg F2 here. For p equals 5, this is new. And this was really the heartbeat of this paper. This was, and I'll show you where this comes in. P equals 7 and larger, I think should have been considered to also be known maybe for n equals 2. And that was not the heartbeat of the paper, but it was an observation that nobody else has done before. So I think we're quite happy with that as well. Now, what about the dimension? Here I wrote you a formula for the dimension. That's pretty easy. For p equals 5, or even in general, I guess, even in general, the dimension of this homology group for any p is quite easy to compute. I say is very computable. Is this an English sentence, Graham? Is very computable?
It is.
Good.
And I mean, you probably said before that there can be no torsion in this.
There is no torsion in this group. I mean, this is the top homology of a simplicial complex.
The congruence of
This, I don't know if it has torsion. I don't think it does. We don't see any torsion, but I don't know of any torsion. Yeah. So certainly for 5, 3, and 2, it does not have any torsion. For p equals greater than 7, everything we see doesn't have torsion. Yeah. So this is very computable. In particular, I can compute. What I did, I was punching this in for p equals 5, and I was able to compute all of these for n smaller equal to 200 in 1 minute. You could not do this for n equals 3 and p equals 7 overnight. So just as a comparison. So this is, you should consider this as a computation. This is computed. That's what I'm trying to say with this. There's not much more to know about the right-hand side. I mean, there are other things, but this is kind of the point that I'm trying to make with this. Okay, maybe is a good point to have questions if there are any. Yeah.
There is no formula such as
like this.
Yeah.
So we have a recursion formula that computes the dimension of this quite fast. It's not quite as nice as this one. I don't know. Maybe yeah. If I give you the combinatorial recursion formula, maybe you are able to actually find an what's it called? A way of writing it without recursion. Explicit. No, this is free abelian.
Yes, but the TNQ of gamma and p, is it still the Steinberg module of the? I mean.
No. So the Steinberg. this is not the Steinberg module of F, so of F5 exactly. This is much bigger, or much is considerably larger. The problem that, or why is this the Tietz building? Well, because so the units of Z are just plus and minus 1. And the units of F3 are also just plus and minus 1. Now the units of F5 are not just plus and minus 1, you also have plus and minus 2. And that creates more stuff. So in some sense, so this is in some sense so how would you describe this? This is also sort of like a building. It's we call it an oriented building, where instead of all subspaces, you take subspaces with an orientation. So like a plus, yeah. So you get, for 5, you get two subspaces for each subspace. You should imagine for a line you get, well, for a line in F5 to the n, you get 4 generators of that line, and 2 of them are being associated and the other 2 are being associated by plus minus. But then you have two different versions.
And
anyway,
so, every time you, I mean, for 7 you have 3.
Yeah, exactly. Yeah, precisely.
Just a question.
Yes, please.
On the right-hand side of your theorem, like you said, for p equal 5, you can compute the dimension.
Yeah, and for p equals 7, we can compute this as well. Yeah.
Okay.
Yeah. This has nothing. This side here this is not harder for other primes. The left-hand side is harder for other primes. This is the easy bit.
Okay.
Yeah. And I mean, we still get, maybe I should point this out as well, through us proving that this is surjective, we improve lower bounds that were known before. And we actually, how do we prove that it's not injective? We find something in the kernel. So we find even more stuff in the kernel that improves the lower bound even more. But we do know that that's not enough to find all of it, unfortunately, even though we have something in the kernel. We don't have the entire kernel, that's for sure.
Would you like some information on the kernel, like the rank, or?
Yeah, but I mean, it's too technical.
Okay.
Yeah. And maybe I should also point out that shortly after we published this, Joachim Schwärmer came out with a paper improving our lower bounds for these other primes. So there is active. There is some. I'd be very interested in trying to figure out what is actually happening for these larger primes. Okay, let me give you a little bit of an idea of what's happening by looking at n equals 2. This is actually quite interesting, I think, and maybe something that is quite good to know in general. What happens there for congruence subgroups or any subgroups of SL2Z? Well, there it is that the classifying space of this group is the modular curve, the so-called modular curve. And let me take P is at least 3 and prime. Now this is, what is the modular curve? A curve is meant in the complex sense. So this is actually a surface, a Riemann surface. So this is an orientable connected Riemann surface. Or, I mean, you can, whatever, surface. And in particular, it has genus P plus 2 times P minus 3 times P minus 5 over 24. And it has has punctures in bijection with this. So let me draw a picture. So I have for p equals 7, this means genus 3. And I think, I forgot, didn't write it down here. I think 24 punctures. Some number of punctures, yeah? I didn't count how many punctures I put there anyway. So in particular, this means that, well, if you have one puncture and you draw a cycle around this one puncture, then that one cycle is actually a boundary because you have the rest of the surface to bound it. But if you have 24 punctures, then that means these 24 punctures, if you take the cycles around them, generate a free abelian group of rank 23, one less. So in particular, the one homology that is generated by the punctures corresponds to the reduced zero homology of this thing. So for p equals 7 and n equals 2, you can see now, oh, there is a surjection, and the kernel is exactly the homology that comes from the genus. Yeah. So in particular, this means that H1 of gamma 2p, well, there is a surjection onto the reduced homology of this 2. 2, and there should be a p here, mod p. This is a surjection, and then the kernel of this is precisely the homology that comes from the genus. So that is z to the p plus 2, p minus 3, p minus 5 over 12, because I get two classes per genus. So so for n equals 2, we understand this completely. And actually we are able to compute this with our methods. We wouldn't need this known result, but we can compute this with our methods. Okay, so in that sense, this is not us, like this is not new, this is known. And so in that way, it was known that the Lee-Sharver conjecture was wrong for n equals 2. Okay. Yeah, sorry. Maybe is there a question about this? Because this is still the overview part. Okay. Let me go into the proof a little bit of this. Yeah. So I wanna explain a little bit how this proof works, and we'll see how far we get. But so the main connectivity result, and you've always seen now connectivity result. You always see now that, oh, we construct some simplicial complex and then prove that it's highly connected, and then we use that to prove our result. That's what we do for a living. Yeah, and so the main result here is that, as I already said, this is a simplicial complex, and this is n. So maybe I should say this here. This is n-dimensional, and you remember from our last lecture, Church and Putman proved that this is n-1 connected. Now, this is not true in general anymore. This is in general, this is, with this quotient, is only n-2 connected. all primes. And n minus 1 connected for p at most 5. So this is really the complicated part of the paper, is showing that for p equals 5, this complex is n minus 1 connected. Yeah, that was the hard work of this paper, and it paid off in the sense that we were able to then compute exactly what gamma n5 is, the cohomology. For n equals 2, it's clear that it's not simply connected because you have genus. So maybe that's helpful to say. Maybe remark BA2Z mod gamma 2p is the modular curve with the punctures filled in. Punctures filled in. So in other words, this is the Satake compactification of this local symmetric space. This is all the same thing. Modular curve is the same thing as the locally symmetric space, and then this gives you a simplicial complex structure on the Satake compactification. Yeah, and the punctures here are literally where the vertices of this simplicial complex lie. Anyway, so you can see now for p equals 5, there is no genus because p minus 5 is 0. But for p equals 7 and higher, you have genus, and that will show you that it's not local, that's not simply connected. All right, now I will take this off so we can see this result. Let me first show surjectivity. So we do know already that Steinberg Q gamma is equal to the relative homology BA n gamma BA n prime mod gamma. Yeah, this is what we said right here. So this is then gets out the homology. Here, I guess this follows immediately there. So this is what we already know. And then, well, we can again use the long exact sequence to get a map to Hn minus 2 of BA prime n gamma. And now in general, the next group is always 0 here in this long exact sequence. So this is always a surjective map. But the group beforehand is not necessarily a 0. So we only get this as a surjection. And then you had a map from BA prime, or from the subdivision, I guess, of BA prime to the Tietz building. And so you also get a map to that mod gamma. And here again, you can use one of these Quillen lemmas to show that this is also surjective. So this is in some sense the same proof as Jenny presented, just backwards. Yeah, because before we knew that this was Steinberg, and then we went backwards to show that this is a presentation. Now we know this gives me a presentation of Steinberg covariance and show that that's actually the same as this homology group. Kind of funny how that works. Okay. Proof of injectivity. Well, it's the exact same proof, except that now in the long exact sequence, we do know that this is, that the group that comes beforehand is 0. I'll just say same proof. Now in this case, for p equals 5, this is an isomorphism because this group is 0 because this thing is n-1 connected. And similarly, we can also say this this map here for n equals 5 is an isomorphism because we can use the equivalent lemma that I told you about in the last lecture, because now the fibers here are just going to be smaller versions of these BAN mod gamma, and they are also going to be one higher connected than before. So again, here we have a bijection. So that will give us injectivity between this and this for p equals 5 or p small equal to 5. Now, what happens for non-injectivity? So let me say, well, we have that this is a surjection. We don't quite know if this is injective or not let me say the following. For n equals to 2, for n equals 2, this is not injective because we have exactly this homology coming from the genus right there for n equals 2, and then this is an isomorphism here. But for n greater or equal to 3, we don't know whether this is 0 or not in the long exact sequence. We don't know whether this is injective or not, but we do know that this map is not surjective. Sorry, not injective, I meant to say. Is not injective. So of course, the whole map can't be injective. And where does this come from? Now here, this is the complicated part of the spectral sequence. But now I have 5 minutes, so I maybe say something about the spectral sequence finally. So if you have two posets, if you have a map of two posets, then there is a spectral sequence, and this spectral sequence looks like this, and I'm going to use a reduced version of this spectral sequence. You take the homology of the poset Y, and you have a coefficient system that sends Y to the reduced cohomology of the poset fiber. And then this this spectral sequence converges to the relative homology, or the relative homology of this map, or the mapping cone of this map. Okay? No, not okay, but so in particular, so what does this mean? In the spectral sequence, you can write this now as a table. Here you have P, and I use P for two things, but that's going to be what it is now. In the spectral sequence now, we have certain entries, and through what is written here and the connectivity statements, we find out that that in the spectral sequence there are only two diagonals that are non-zero, this one and this one. And a diagonal corresponds, so in the end, a diagonal corresponds to the homology of what we want to figure out. And the whole point of this of this proof is that actually, well, this entry here is 0 as well, and then this entry here is not 0. But in a spectral sequence, you have certain differentials. So in the E2 page, for example, you still have this thing that you have to get rid of. I understand that I'm not explaining spectral sequences for anybody.
So what's the homology of F? F is a map of posets.
Yes. So I mean, you should, if you view this as simplicial complexes,
yeah,
then, or like just like take the associated simplicial complex, and this is a simplicial map, yeah, and then you can take the mapping cone. Yeah. Anyhow, what comes out of this is that there is this. So this implies there is a non-trivial. Let me see that I get this right. There is a non-trivial homology of n in degree n-1 of this thing. This comes out of that, because this is 0 and this is not 0. This is kind of what comes out of there, and I certainly don't have the time to explain how spectral sequences work. But what is that good for? Well, that means that if you take the long exact sequence of these, and maybe I should have mentioned that this poset corresponds to this simplicial complex, and this poset corresponds to this simplicial complex. So that means now in the long exact sequence, I have h and -1 of the Tietz building mod gamma. Then I get to h n -1 of f. And then I get to h n -2 of, maybe reduced or something, of BA prime gamma. Then I get to hn -2 of tn q mod gamma. And then I get, maybe I get to this. Now, this here is 0 because, as you can see over here, there's only zeros. We just proved that this thing here is not 0, but this thing here is 0 because there's nothing in those dimensions. Oh, wait a second, I'm talking until when? Until 4? No, until 15. I should have taken so much more time to explain this. Maybe we'll take an early break. Or lots of questions, but there's maybe there's not that much. Yeah, we'll see. I see. Okay, I can definitely slow down. what you see now is, I mean, you can see from this, oh, this bit here is surjective. You can see that from here. That was part of the surjectivity proof here. But you can see now that it's not injective because there is something injected, it's something non-zero injecting into it. No reason to hurry, huh? Okay. So this, let me maybe say a few more words about what this thing is right here. And then we'll just go to questions and either take a longer break or start a little bit earlier with the exercises, okay? So what is this? What is this little bit here? Yeah, this is, well, from what we get over here, this is H, let me get this right. This turns out to be, I mean, if you just plug it in, it is h n minus 3 of excuse me. That will also be edited out, please. Of y with coefficients in y going to h1 twiddle f small equal to y. But one can actually show that this is the same as the sum over all. So what is y? Y is the Tietz building. I mean, a version of the Tietz building. And so an element in there is something that has a dimension. So one can show that this is equals to 2 and h twiddle of n minus 4 of y greater than y tensor. So where this is just another way of saying n minus 2 of q mod gamma, n minus 2 p. And over here we have h1 of BA2 mod gamma. So why is this non-zero? Well, we definitely know that this bit here is non-zero. That's something we can easily compute. I said that in the beginning. And then we also know that this bit here is non-zero. This for gamma, because this is really just the genus. This is the cuspal cohomology of these gamma 2s. And so that's really where this all comes from. I got completely confused by what I wanted to do and in which order, what time I have. So I'll just quit while I'm behind. Thank you for your attention.
So we have at least 10 minutes of questions.
We have to fill the time. Come on.
Any question?
Yes, please. In this spectral sequence, we can very easily compute what the things are on these diagonals. Compute. No, so sorry. On these diagonals, what you will have is always h n minus 1 of gamma of b. Sorry. On this diagonal, you will always have E PQ2, where this diagonal here is n minus 2, P plus Q equals n minus 2. You will always have something like this. So some direct sum of some homology P minus 1 of T P minus 3 mod gamma P minus 3. So this is very easy to compute, but then you have H Q of BA Q plus 1 mod gamma, and this we don't know what that is other than for n equals for n equals 2. So this we don't know what that is. So we can't really, in that sense, we cannot compute what's above here. That is problematic. Here on that side, it's even harder, because in that side you're gonna have HQ of BAQ coming in, and this is even harder. This we really have no idea what that is. So even if we had, even if we knew what these differentials did, I mean, you have all the differentials, possible differentials here, maybe we wouldn't know. We don't quite know what these different groups are.
So you cannot describe at least formally what the differential.
I think formally we could probably describe what the differential is. I don't think that's a problem. No, but so this spectral sequence will only compute BAN prime, and as I said here, this bit is maybe also not injective. So, and especially for n equals 3, we know that this bit is not injective either. So this for primes larger than 5, we're quite a bit away of what exactly is going on, unfortunately. Yeah. Some hope was so at some point we hoped this this kernel here will tell us, will only give us the cuspidal cohomology or something, or like the interior cohomology of this group. But we looked at this more closely for n equals 3, and it turns out to be completely wrong. So there is homology coming in this kernel that is actually at the boundary. So it's still a little bit of a mystery.
So any other question, or 5 minutes to answer? We have time for that.
Yeah, plenty of time. It's nice to have something a little bit earlier over sometimes, right?
Yes. So more questions? If not,
I mean, we have another question answered.
Yeah.